Who is here for their first Python conference? Excellent. Okay. And who's here for your first PyCon Italia? All right. For your first, excellent. That's wonderful. Okay, so congratulations, because you've picked a wonderful community to be a part of, and you've picked an excellent conference to sort of be introduced to that community. So congratulations on that. That's wonderful. I will talk about a few projects in the course of this talk. What they have in common is that they all have a Python code base. So if we're continuing with a show of hands, who in here has heard of, has a rough idea at least of what Ansible does? Okay, plenty of Ansible people. And I mean, you know, not necessarily being an Ansible developer or being an Ansible contributor, but just you know generally what it is and what it's about. Okay, Ansible. Who in here has heard of or knows a little bit about OpenEdX? Okay. Who in here has heard of a project called Tutor, also in the OpenEdX space? Python project named Tutor in the OpenEdX space? Nobody? Okay. And who in here has heard of Django? Excellent. Excellent. So that means you're in the right room, and I'm in the right room, because I have something new for all of you, and I have something familiar for all of you. Okay, let's get started with Ansible. So this is a Python conference, so considering it's a Python project, as we've established, it's relatively safe to assume that at least a majority of people knows about Ansible, at least to some degree. And if you have ever used Ansible before, then you may have come across the Ansible GitHub repository. So the Ansible GitHub repo has Ansible's project history all the way back to February the 23rd, 2012. That's when the Ansible project started. The first commit in the Ansible GitHub repo just reads Genesis. That's all it says. And there is something up here in the repo description that I think has been there pretty much from the get-go. It has been mostly unchanged since 2012, or at least I remember it to have been there for as long as I've been using Ansible. And I got my start with Ansible relatively early on, about 2013 timeframe. Now here's what it says. I'll quote this for you. It says, Ansible is a radically simple IT automation platform that makes your applications and systems easier to deploy and maintain. Automate everything from code deployment to network configuration to cloud management in a language that approaches plain English using SSH, secure shell, with no agents to install on remote systems. Now I think of these, the second, the longer sentence, that may be a little more recent, but the first one, that's the one I think that has been there from the get-go. So it says, Ansible is a radically simple IT automation platform that makes your applications and systems easier to deploy and maintain. Radically simple. I have my doubts about that. So for those of you who are more familiar with Ansible, if you had a junior colleague, and you're an Ansible shop, say, and you had a junior colleague that's just starting out, and you're introducing them to Ansible, would you describe Ansible to that person as simple? Probably not, right? I think you wouldn't. But where does that come from? Where does that claim come from? Well, first of all, when we talk about simplicity, when we talk about whether or not something is simple, the question that you're always implicitly asking is, compared to what? And like I said, this statement has been around since 2012 when Ansible was first started. So in 2012, what you would compare Ansible to in terms of simplicity was the incumbent in its problem domain, in the server automation space, which of course at the time was Puppet, and Puppet had been around since 2005. And when you compared what Ansible could do to Puppet, Ansible was simpler at the time, largely, or at least in part, because with Ansible there was a jolly good lot of things that you couldn't do, that you could already do with Puppet. So there was simply a lot less that you could do with Ansible than you could with Puppet, and so of course Ansible looked simpler. So to summarize that bit, new systems frequently just feel simpler to you just because they can do less than established ones, specifically the ones that they're set to replace or trying to replace. And that's largely due to the fact that I'd say for about something like 90% of software systems, let's say distributed software systems, you can probably design a replacement in 6 weeks and then bang out a first release in 6 months and then spend 6 years ironing out the kinks and edge cases and corner cases. And perhaps for another 5% of software systems, the number is actually 10 rather than 6. So 10 weeks, 10 months, 10 years. But as a system grows and it adds more features and more capabilities, it's subject to a rather interesting phenomenon which really contributes to its growth in complexity. Who in here has heard of or read this article, The Configuration Complexity Clock by Mike Hadlow in 2012? Has anyone read this in this room? No. Okay. That's a real problem, I think. So what I'm going to be talking about next is from an article called The Configuration Complexity Clock, written by a guy named Mike Hadlow, who happens to be a C#.NET developer. So it's absolutely not a community that I'm a part of. He lives in the UK. He wrote this in 2012. It's one of those things that I think everybody who's in software engineering, specifically every software engineering manager, should have read, but very few actually have. In that way, it's not entirely unlike Fred Brooks's Mythical Man Month from 1975. So here's what this says. Here's what the configuration complexity clock talks about. It says to think of the development state of a system as a clock. So basically, the hands of a clock going around the clock face. So initially, we start out at noon, right? And when the system is at noon, or midnight, if you're a night owl, if you're wired that way, you start out with everything being hard-coded. So to make the system behave differently in any way, you have to change the code. That's sort of step number one. That's noon. And then, as the system evolves, we get to the point of saying, well, some ability to configure things would be really good. And we add configuration values. So those could be variables in a config file. They could be additional options or arguments for a CLI. They could be environment variables for a container. Of course, the environment variables for a container bit wasn't in the original article because nobody did that in 2012, but it's fundamentally the same approach, the same principle. So that's 3 o'clock. And then we begin to add some relationships between our config options. So it eventually becomes a rules engine. So as an example, you might be writing a CLI, you might be writing a command line interface, and that CLI has multiple subcommands. And now you're adding some kind of a mode switch that makes all or most of your subcommands behave differently based on how that mode switch is set, right? So you've effectively applied something akin to a rules engine. You're at 6 o'clock. And then all of that eventually morphs into a domain-specific language, or DSL, and we're at 9 o'clock. And then you realize that managing all that DSL by hand is too unwieldy, and you end up writing some code that generates that DSL for you. And it's noon on the configuration complexity clock again. And there's something that Mike Hadlow wrote in 2012 in that article that from today's perspective looks almost cute. So he wrote in 2012, to be honest, I've never seen an organization go all the way around the clock, but I've seen plenty that have got to 5, 6, or 7, meaning they've got about halfway around, and feel considerable pain. That's 2012. So if you look at that with the benefit of more than a decade's worth of hindsight, this is definitely an oh my sweet summer child kind of moment. Because since that article appeared, since it was published, there have been so many organizations that have taken multiple laps around the configuration complexity clock. And that includes a great many open source software projects. I've seen things that you people would not believe. And interestingly, for those of you who use Ansible kind of heavily, this is a great background for a picture, thank you. So for those of you who are using Ansible more heavily, you'll find that with Ansible specifically, there's something really interesting about it because Ansible, it kind of embodies the configuration complexity clock, not just in terms of the development and the evolution of the project, but also about the development and the evolution of an individual Ansible user. Okay? And in that way, it's really fascinating because if you're an Ansible novice, you start at 12 o'clock, you start at noon, you write a straight-up playbook. It's very simple. It does things, everything's hard-coded, you know exactly what it does. Then you realize it would be nice to make some values configurable. So you define some, and you perhaps add a vars file. You're at 3 o'clock. And then you create your first inventory, which aggregates hosts and adds them to groups, applies roles, sets variables to them, and suddenly you've built a crude rules engine. So now you're at 6 o'clock. And then you notice you can write your own roles, and they can have defaults, and both the roles and the defaults in those you can use like these Ginger2 expressions, and now you have this very peculiar, like really loosely defined but clearly domain-specific language, namely this weird mix in Ansible of YAML and Ginger2 and some straight-up Python sprinkled in. So you're at 9 o'clock, and then you figure out, well, hold on, I can discover most of what I need for my inventory automatically, so I don't need to maintain it manually anymore. And also, you've got some Python chops, so you write a dynamic inventory driver, and you're back at noon again. And then, of course, the cycle doesn't stop there, because now your inventory driver grows configuration options, etc., ad infinitum. So takeaway number 2, quit pretending that you can escape the configuration complexity clock. And just so I'm abundantly clear here, this is by no means limited to Ansible. The configuration complexity clock is everywhere. So if you look at other configuration platforms, say Terraform, for example, it beelines straight to a DSL. So maybe they hoped that they could sort of escape the clock that way. But then, of course, people got tired of maintaining HCL by hand, and then you got TerraGrunt. And then the Kubernetes manifests, those are another example, because people got sick of hacking those by hand and now use Helm to generate those, etc., etc. There is no escaping the clock. If you think that your next iteration will solve your complexity problem, it won't. It will just take you further around the clock, and eventually you're going to end up at noon again, and the cycle is going to start over. So just to be very clear and to illustrate the point further, let me show you examples from another project, lest you think I just cherry-picked Ansible or I'm trying to pick on Ansible or anything like that. So OpenEdX. Okay, so I can't necessarily assume that everybody's familiar with this Python project, so I'll explain a little bit about what it does. OpenEdX is a general-purpose learning platform. So if you roughly know or have used at some point the Moodle platform, right? If you've used Moodle before, and you have a rough understanding of what Moodle does, you now have a rough understanding of what OpenEdX does. It serves pretty much the same problem domain, except that where Moodle is, of course, a PHP code base, OpenEdX is a Python code base. So this project came out of a platform originally developed at MIT. There was an initial collaboration from Harvard and Stanford universities. 11 years ago, it was released as an open source project under the AGPL, the Affero GPL. So it's also been around for more than a decade. It's actually roughly the same age as Ansible, but that's pure coincidence. And it has grown sort of far beyond the academia space where it originally came from. So there's businesses using this for professional training. I use OpenEdX in my day job as somebody who writes courses on the OpenEdX platform, who helps maintain an OpenEdX platform, and I'm an occasional contributor to the project. And at its core, OpenEdX is really a Django application, or rather, it's a whole array of Django applications that all work together. So it consists, for example, or it contains an LMS, a learning management system. That's what you use as a learner interacting with the platform. It has a courseware management and courseware authoring system, so that's what instructional designers and course authors use. And there's lots more adjacent components, but it's, like I said, it's basically a bunch of Django applications all working together. Now, the reason I'm mentioning it here is that OpenEdX as a project is full of great examples of how complexity, once it has been injected into a project or system, does not go away, and it does not recede either. Complexity is always here to stay. And as a corollary to that, no, you cannot make it go away by abstraction, automation, or encapsulation, because all of what they do is abstract, automate, and encapsulate complexity. They don't make it go away. Quite the contrary. Now, before I do want to reiterate, if you like. I don't mean to pick on OpenEdX at all. I don't, just like I didn't mean to pick on Ansible either. I do not want to insinuate that there's incompetence at work in these projects. Quite the contrary. I'm perfectly convinced that what I'm talking about applies to substantially all collaborative software development projects. If anything, I think it's probably a lot worse in proprietary ones than in open source software projects. But the fact that projects like Ansible and OpenEdX and Tutor, which I'm going to get to, and so many other projects are open source, simply enables us to look into them and investigate and analyze these things and learn from them, which is a good thing, obviously. So with that said, let me give you one of many, many illustrative examples of the permanence of complexity from this project. So early on, the OpenEdX folks decided the platform needs some kind of a shared file system. So courses in OpenEdX are essentially files. So they're imported and exported as tarballs. And then they need to be stored somewhere on the back end where all the front-end servers can access them. So this data must be accessible from multiple locations. There is an architectural requirement that follows from this, that we need some kind of a shared file system somewhere on the back end. And apparently the developers at the time considered NFS to be a non-starter. They didn't want to use that. Again, we're talking 2012, 2013, that kind of time frame. They also looked at GlusterFS. They considered that. They rejected it, didn't like it. They also didn't trust CephFS. That part is totally reasonable because at the time, this was 2012, this was about 3 years before CephFS became sort of production grade. Okay, all fine. But what they eventually went with was this very strange, kind of, sort of, but not quite like a file system abstraction called GridFS, which is a MongoDB feature. And with that, they made MongoDB a core component of their platform. Now, I got my start with OpenEdX about 2015, so this would have been about 2 years after this architectural decision was made. And so about 2 years after they made this decision, they realized it was probably not a great one, architecturally. So even at that time, about 2015, the opinion among the developers was, whoops, this was a mistake. We should really get rid of MongoDB. It doesn't really make sense to have that dependency. And now we're about 10 years after that, and the project is now at the stage of, well, we'll try to get rid of it really soon now. So the project still has not managed to sort of kick that dependency. And it wasn't for lack of trying, I want to be clear about. There was an attempt to refactor all of this storage backend effectively out of the OpenEdX core, make it a separate application, which they called Block Store, another Django application which would be implemented using DRF, the Django REST framework, would interact with the front end via a REST API. It would use S3 storage or basically anything compatible, probably even anything that Django storage is supported. So you have a fairly large number of potential backends. And then they found out that that came with really bad performance. Like that kind of architecture incurred a really bad performance penalty. So they put that back into the core. And they're still not rid of the original GridFS thing. So now they've got another thing in the core and MongoDB, which of course is a burden on administrators because they need to track that for updates and manage that and whatnot, and you have no net reduction in complexity at all. Because no matter what you try, complexity does not recede. And here's another example, also from OpenEdX. OpenEdX did something that was truly great from the get-go, which was that from the beginning, they didn't just open source the platform code itself. They didn't just open source the Django applications because, number one, these Django applications all work together in a relatively complex manner, but they also have other requirements. So one was the shared file system thing that I talked about, but you also need a relational database, you also need memcached, you also need a Celery backend, so Redis, for example, and so on. So if they had just thrown the platform code over the fence, it would have made the adoption of OpenEdX tremendously difficult, but they didn't do that. Instead, they also open sourced all the tooling that was required to deploy the platform in an automated fashion. And this was largely based on Ansible. At least initially, they also had officially supported CloudFormation templates, so you could get your start in AWS. You could basically bootstrap the platform in AWS, and from there on, do the rest of the configuration with Ansible. But basically, building this on Ansible playbooks meant you could effectively run OpenEdX in anything that gave you a virtual machine. You could run it in AWS, you could run it in VMware if you like, you could run it in Azure, in OpenStack, in wherever. On bare metal, if that's how you roll, fine. And that allowed you to build an architecture in an automated fashion, build and maintain an architecture in an automated fashion that looked like this. So you had an automatically deployed 3-node backend, in a highly available MySQL and MongoDB cluster that also hosted the other shared services like memcached and your Celery backend. You then had as many front-end servers as you wanted. The front-end servers were effectively stateless. So it was basically just running the stateless bits of Django. The way that you would build out and scale your platform would be you pre-installed one of these front-end VMs. You basically populated the whole thing. You took a snapshot of that, and then you deployed as many or as few as those as you'd liked. If there was an update that you wanted to include, you just refreshed that snapshot. You perhaps did so on a schedule of like once a month or twice a month if there weren't any critical updates. And scaling the front end out and in was really easy because you just spun up additional front-end servers, you plugged them in and out of a load balancer, fine, great. It was really neat and cool and useful. But of course, as it grew more features, it became more complex. And this made contributing to this set of Ansible roles and playbooks and so on a little bit challenging, particularly for new developers. So again, as with the MongoDB GridFS versus Blockstore bit, people desired simplification. And along came a project that went through a few names. Now it's called Tutor. But what that project did that emerged was enable you to run OpenEdX in Docker containers. Because, of course, containers make everything simpler, don't they? Containers simplify everything. And of course, just as with the story of Ansible and Puppet that I alluded to at the top of the talk, it was initially simpler because it could do a lot less. It was really simple to sort of spin up an OpenEdX environment with Tutor that didn't do much. But once it actually grew to a point of having feature parity, it was every bit as complex as the old stuff. And I'd say that as of today, it's also no longer significantly easier to contribute to this deployment platform than it was to the old set of Ansible roles and playbooks. So what Tutor actually does is it generates Kubernetes manifests and Docker Compose definitions for you, and it generates Docker files for you. So guess what that is? It's one more lap around the configuration complexity clock because this is code that generates a DSL for you. Or actually 3 DSLs, 2 of them YAML. But Tutor also illustrates another very classic, typical problem in complexity management, which is making complexity someone else's problem. So in Tutor, the lead author maintains a policy that the core project, will only accept new features if it benefits a large proportion of users. He doesn't say the majority, he just says a large proportion. So if you write a new tutor feature, you write it out, you don't just suggest it, you actually write it and you send a pull request. Then the author says, well, no, I'm not going to merge your pull request unless you can demonstrate that this will actually be useful to about 30 to 50% of the user base. And then, if for anything else, Tutor has a plugin system that allows you to incorporate any feature you like by writing a plugin without touching the core. Now, that sounds eminently reasonable, doesn't it? So what the author is trying to do, and I think this is a perfectly worthy cause, is he's trying to make the project no more complex than what's needed for most users. Great. But what you end up with is the core of the project being essentially unfit for purpose without plugins. So even today, we're in a situation where you cannot roll out OpenEdX without using some plugins, which are now core in all but name. And the complexity of managing all those plugins and making them work together, all of that ends up in the user's lab. So in the OpenEdX platform admin's lab in this case. And in my experience, it's not uncommon to have to run something like maybe 10 to 15 tutor plugins to run an OpenEdX platform that can do the same as the stuff that you ran with the old Ansible playbooks. And by the way, Ansible itself has this problem too. You know, how it grew Ansible core and then collections and so on. Like we have exactly the same thing. I see people nodding who are apparently working with Ansible a lot, right? So that leads us to our next takeaway, which is that pushing downstream complexity does not reduce it. It just makes it somebody else's problem. Now, I want to be clear here. Of course, if we're the developer of something, or if we're part of the development community of something, of course, we would prefer if things were simple or simpler if given the choice. For us, the people building something as well, not just for the people using that same thing. But we do need to keep in mind that there is a ratio of upstream to downstream. There is a ratio of developers to users, and that's kind of difficult to ascertain. But, you know, like for example, if you look at Kubernetes, Kubernetes is a very large collaborative project. It has on the order of about 10,000 contributors. About 10,000 people have landed a patch in Kubernetes at some point. And now it's really difficult to estimate like how many Kubernetes clusters are out there in the world, but it's probably like single-digit millions by some estimates. So the upstream to downstream ratio, and it's also difficult to say how many Kubernetes clusters are managed by one person. It's all a bit difficult math, but we can probably assume that the upstream to downstream ratio is probably something like 1 to 1,000. So one developer for 1,000 users. If you look at curl, curl in contrast has on the order of about 1,000 committers, and it definitely has more than 1 billion users. Like if you have a smartwatch, that thing runs curl, right? If you have a car that was built in the last 10 years, that thing runs curl. Not to mention like the phone and your laptop and everything, right? So there the ratio is probably 1 to 1 million or even higher. So 1 million users for each developer. So making things simpler for some number of people while making it more difficult for orders of magnitude more people, that's not a net win. That's not a reduction in complexity either. So what can we do really to simplify, to reduce complexity? And at this point, I really hate to bust your bubble if you've been living in one, but the answer is probably nothing. And I don't say that lightly because I do have physics on my side to back me up. Okay, so bear with me for a second. We're going to go back to computers in a minute, right? But as far as we know, there are 3 fundamental physics theories that combined explain the whole universe as we know. No, they explain everything that we know about the universe, which is the whole universe. And physicists would love these to be 1, but they haven't managed that yet, so we need 3. And those 3 theories are general relativity, that explains mass and energy and space-time and gravity, being one of the 4 fundamental forces in nature. Then we've got quantum mechanics with its standard model. It explains the other three fundamental forces of nature, namely electromagnetism and the weak force and the strong force. And that in turn explains structure and the nature of atoms and ultimately chemistry and with it biology and with it life. Helpful. And finally, we have thermodynamics, and that, among other things, explains heat and work and so on. And thermodynamics has this famous second law, the second law of thermodynamics. We can state this in various ways, but in one modern form, we say the total entropy of a system never decreases. The total entropy of a system never decreases. What does that mean? What is entropy? Entropy is the degree to which something, a system, is disorderly. And so more precisely, entropy is the number of possible configurations in a system. And of course, the more possible configurations that we have in a system, the more probable it is that the system is currently in one that isn't useful. Right? So a disorderly one. But in effect, the second law states that any system can stay just as orderly as it is now, or it can become more disorderly, but it can never again become as orderly as it once was. And the normal state of the world is that things keep getting more and more disorderly. And there's multiple standard examples of this. You can mix two paints in a bucket, but you can never unmix them. You can scramble an egg and cook it, but you can never return it to the original protein structure. And there's a curious consequence from this that kind of the physicists kind of pore over, which is that this constant growth in entropy, this constant increase of entropy, is our best explanation why time always goes forward. So, because it's a little bit weird, right? Because since Minkowski, we know that space and time are really one and the same thing. They're part of this four-dimensional thing that's called space-time. And since Einstein, we know that general relativity applies to all of that. So both space and time are influenced by mass. The principle of general relativity applies to all of those. But motion through space is reversible, whereas motion through time isn't. And that's very peculiar. It doesn't really make sense in the whole concept. Because if you have some motion through space, you can describe that with a vector. You flip the sign of that vector, boom, motion goes backwards. We don't have that option in time. We're great at time travel, but it only works forwards. And at a speed of 1 second per second. It always goes forward. And this inextricable linkage between the growth and entropy and the passage of time is really one of the best possible explanations we have for that fact, namely that time always moves forward, that we have this thing that physicists call the error of time. So reducing entropy is just as realistic as traveling backwards in time. But we can do things to speed up the growth of entropy, and then we can do the opposite to sort of slow it down. So what are ways to drive entropy in the kind of systems that we typically manage? I told you we were getting back to computers. So what drives disorder? What drives entropy in software systems? Now, of course, in principle, every addition to a software system increases entropy because whatever you can add can go wrong. Simple. But there are some things that are extremely common, and they really increase entropy much, much more, such as adding features without gating them behind a feature flag. Because if you do this, once the feature flag is rolled out, you have no way to undo it. And not only that, but any unexpected fallout from your change is not only here to stay, but it continues to accumulate, which makes the mess harder and harder to fix. Adding features without test cases means when something breaks in a later edition or in a later change, you have no idea what really broke and when. Adding features without documentation means you have no record of how the system's even supposed to behave. So you can't even tell if something broke or not. Or you can have arguments with people about it. Is this actually breakage or not? Refactoring without first achieving feature parity. You know this classic thing, oh, we're going to rewrite this bit, but this little bit of it we no longer need. So we can leave that out of the rewrite. That means you're going to run 2 or more parallel implementation strands essentially forever. Because you can be damn sure that the one thing that you thought you could leave out of the refactoring broke at least one person's workflow. And finally, violations of the principle of least astonishment, or polar, which means the system behaving unintuitively, that's just going to screw up everything forever. So what does that mean for the people responsible for those systems? What is their job? What is our job? If you're responsible for a system, it's your job to slow the growth of disorder in that system. And I use the term system really, really broadly here. It could be a software project. It could be a platform you manage. It could be an organizational unit you are responsible for as a manager. You will never be able to reduce disorder, and any attempt to do so pits you against a most fundamental law of physics. Because laws of physics are like terrorists. You shouldn't attempt to negotiate with them. But you can do your damnedest to slow it down. So here's what you can do. Never land a change without documentation. Always make sure that the documentation update happens simultaneously with the change. Docs define how the system is supposed to behave. Always follow the principle of least astonishment. Make sure that the system behaves in a way that intuitively makes sense. And no, following the first item in the list is not a free pass for this. Because of course, it is 100 times worse for a feature to behave counterintuitively and not be documented than to behave counterintuitively and be documented, but it's 100 times better for the system to behave intuitively and be documented. Never merge a feature without a corresponding test case. Always include the test case in the patch, in the very patch that merges the feature. Never send a new feature to prod without a feature flag. And when you decide that a particular part of the system needs refactoring, and you think there are some more things that the refactor would touch that you actually don't need anymore, what you want to do is you want to figure out what you think that you no longer need, then you deprecate that, you cut a release, you remove it, you cut another release, and then you refactor what remains. And you do so to full feature parity. And these are all things that any developer, any sysadmin, any operator can do to stem the growth of entropy in the system. But many managers are often exactly the opposite. They are entropy accelerators. They speed up the growth of disorder in the organization. So how many managers have you met that would look at a Slack channel or chat channel or whatever that their team used, and they found that communications were poor and chaotic and it was impossible to follow what was happening, and who would come up with a solution of, let's have more channels? Happens a lot, doesn't it? And that's, of course, more channels that everybody who previously followed just one channel now has to follow, and then the old channel doesn't get retired for 2 years. That's a relatively typical thing. That's not a single example. It happens all the time. And I posit that this is largely due to this weird misguided fetish that we have for this thing called leadership, because people seem to believe that in order to be useful, people must lead and do and direct others, when in reality there's at least 3 productive things that people can do when they collaborate, and one of them is not necessarily better than the others. And those 3 options are to lead, to follow, or to get out of the way. I chose to paraphrase that patent quote because it originally contained more profanity. But really, there's these 3 things that people can do in order to be productive. And people in this context very much includes managers. And I wish managers would sometimes take options 2 and 3 rather than always default to number 1 and then stirring the pot and creating ever more disorder in the process. And I want to also mention another thing that people, including but not limited to managers, very frequently misunderstand, which is there's this thing that we call the KISS principle, right? There doesn't, weirdly enough, there doesn't appear to be much consensus as to what that acronym actually expands to, because some people tend to render it as keep it simple, comma, stupid, exclamation point, as in keep it simple, you idiot. Some people like keep it simple and stupid. So like don't only try to not be complicated, but also try not to be clever. Others still render it as keep it small and simple. So, and it sidesteps the stupid bit, which is kind of polite. But for whatever reason, we seem to agree that we want to keep things simple, and then we also want to keep them either stupid or small. But however we expand this acronym, there's this one bit that's important. It is the KISS principle, not the MISS principle. It's about keeping things simple, not about making things simple. Because the principle as such is quite aptly named, and it is a good engineering principle. It reminds us that it is important to keep things simple while we can, and that is stemming the growth of entropy, slowing the growth of entropy in a system, precisely because it's impossible to make them simpler or simple later on. So that's my takeaway number 6. Aim to keep things simple because you can't make them simple. So to sum up, new is simpler than old, frequently because it can do less. You cannot escape the configuration complexity clock. Really, do make a point of reading that article. It's a good article. It's over 12 years old, but it's really good. Do read it. Complexity does not recede. Pushing complexity downstream does not reduce it. It only makes it someone else's problem. A leader's job, someone who is responsible for a system, it's their job to slow the growth of disorder in the part of the system that they're responsible for. And finally, keep things simple because you cannot make them simple. And that's my talk. Thank you very much. So, okay, we have time for a couple of questions. Do we have questions? Just one question. Okay, I'll take one question. Sorry, I can read it. So the question was, how well do you think the Python project follows the rules you laid out? I do not feel qualified to comment on that because Python is so huge and large and so many things are happening that I don't really feel qualified to speak for the Python project as a whole. But I want to say that people are actually aware of this because they are not afraid to deprecate things, take them out when they're no longer needed, when they're properly replaced, and so on. So my humble opinion is, among other projects, the Python project is doing fairly well with this. But then again, the growth of complexity is a fact, and the only thing that you can do is slow it down as much as possible while staying relevant. That's it. Okay, if anyone has any other questions, then please grab me outside. Thank you very much for your time. Enjoy the rest of the conference. Thank you.